Excuse me, I don't think we can hear anything.
Yeah, my bad. We're getting on it right now.
Okay, no worries. Thank
Okay.
you.
Can you hear anything now?
Yeah, we can hear you now.
Okay, cool.
Okay, dear God. It is starting to echo a little.
Yeah.
So, okay. We're going to hide the phone control.
Awesome.
Sorry about this.
All right, guys. So we were just so Gaussian elimination, that was our first topic in our linear algebra review. And it's essentially used to solve that x vector in our matrix vector operations, or so when you have a equation such as ax equals b, you're able to solve for our vector x using Gaussian elimination. And there's essentially three rules that you follow. So you can either swap each row, you can add 2 rows or 3 rows within your matrix, and then you can also scalar multiply rows in order to get to a certain form. So our reduced row echelon form, which you might have seen multiple times in this course. And when doing these operations, you can tell whether you have a 0, 1, or how many ever solutions by the form of, or by the final form that we're looking at reduced row echelon form. So yeah, that's Gaussian elimination. And then for our the second big conceptual topic, it has to do with span. So the span of a set of vectors is essentially just the linear combination of vectors. The example that I like to use are essentially just our unit vectors. So when you're thinking about our x, y, z plane, like you have a 1 unit vector in the x direction, a 1 unit vector in our y direction, and a 1 unit vector in our z direction. And every single vector in our 3-dimensional space is essentially a linear combination of those vectors. So there's an example here, and it says, for example, the span of v1 and v2 is a set of all vectors of the form s v1 plus t v2 for some scalars s and t. So that's essentially what a linear combination means with respect to vectors, and that is how we define span. Okay. So then there's this idea of linear dependence. So we say that a set of vectors V is linearly dependent if there exist scalars a1 all the way to an such that, or sorry, alpha 1 all the way to alpha n, such that alpha 1 v1 plus all the way out to alpha n vn equals 0. And not all alpha i's are equal to 0. So all that means is when you're able to find a linear combination of vectors that are equal to 0, and these scalars that you're multiplying these individual vectors by, some of them are not equal to 0, then you know that you have essentially a set of linearly dependent vectors. And the converse of, the converse of that is linear independence. So that's a next big topic. So we say a set of vectors is linearly independent if they are not linearly dependent. So if none of your vectors in your space can be expressed as a linear combination of other vectors in the set, then we say that this set is linearly independent. And we'll talk about this idea of basis vectors, but essentially, if you are able to represent a space with a set of linearly independent vectors, and those are usually your basis vectors. Yeah, and then we talk about this idea of proofs, which usually shows up on the exam for at least one question. So it's important to kind of know where this is coming from. But the way to approach proofs is to essentially break it down in this way that we've written out. But essentially, you look at your problem statement and you essentially look at everything that they give you, and you think about all the definitions and formulas that they've given you, and write down whatever you can in that moment, like whatever you know. And so then the second step there is to write out what you know from the statement of the theorem. So if yada yada yada, and then you write down exactly what you want to prove, and you're essentially trying to bridge that gap. So if they give you an if statement and they give you a whatever then statement, then you're trying to use all our formulas and all these mathematical manipulations that we've learned to get to that final form in our statement. So you look at those two statements and you try to essentially convert that form of that if statement into that then statement. So you look at those two statements and write down what is known and what you want to prove and bring them to the same form. And then try it out on, or sometimes it helps to try it out on a simple example. So if you're trying to prove something for an n by n matrix, prove it for a 2 by 2 first. And then manipulate both sides of the claim and be able to justify each step. So a lot of the times this justification is theorems or stuff that you might have learned in during the linear algebra section in this class. Okay, so our next topic has to do with invertibility. So an invertible matrix is essentially a square matrix that has an inverse. That is the very basic definition of it. And if a matrix is invertible, it implies a set of things. So the biggest one is that so when you write your matrix, or when you use your matrix for matrix vector operations, so when it's written out in the form A x equals b, then there is a unique solution for any b. So there's a vector that had that matrix operation done to it for any vector b. And we also know that if A is invertible, then it has linearly independent columns. So that's a definition that we did earlier in this presentation. And then we also know that if A is invertible, then it has what we call a trivial null space. And we'll talk a little bit about that in a minute. So there's a trick that we can use when we're looking at the inverses, or when we're trying to determine the inverses of a 2 by 2 matrix. And so if you have this matrix A, B, C, D, and you're trying to take the inverse of it, then you first determine the determinant of it. And the determinant is essentially AD minus BC. And then you put that in the denominator of it, or essentially take the reciprocal of that. Then you do a couple manipulations to the matrix itself. And and this is essentially like a shortcut for determining the matrix inverse for a 2 by 2 matrix. Yeah. Okay, cool. Moving forward. So the next concept that we are going to go over are vector spaces. So a vector space is a set of vectors that essentially satisfies all these properties below, and we can go through all of them, but the big takeaway from this entire set of things that we're looking at is that our n is a vector space. So I'm just going to go in and read these properties that a vector space has to satisfy. But it says, let V be a set on which two operations, vector addition and scalar multiplication, are defined. The listed axioms are satisfied for every u, v, and w in V, and every scalar, real numbers C and D, then V is called a vector space. So essentially you're looking at the definition of addition and scalar multiplication within this vector space. So it has to be closed under addition, the cumulative property, or the commutative property and the associative property have to hold true, and the additive identity and the additive inverse have to hold true. So this is something that I would recommend everyone taking a second look at and maybe trying problems that have to do with vector space. But the same sort of ideas hold for scalar multiplication as well. Okay, cool. Okay, so the next concept has to do with subspaces. So a subspace is essentially can sometimes be, or subspace is essentially like a little subset of vector spaces. So a subspace contains the 0 vector, and it is A closed under vector addition and closed under scalar multiplication, which should sound familiar from this previous slide. So the idea of closed under vector addition, all that means is if you have two vectors, v1 and v2, their sum v1 plus v2 should also be in our subspace of U. And then similarly for scalar multiplication, if you have any vector v that belongs to our subspace U and a scalar that is a real number, then the product of alpha times v should also be in our subspace U. And this is an idea that I mentioned earlier, but a basis of a subspace is essentially a set of linearly independent vectors that span a subspace. So all that means is if you are trying to define a subspace and you want to give a set of vectors that define that subspace, then you find a set of linearly independent vectors that span the entirety of that subspace, and that becomes your basis vector. So that is the basic idea there. And then the dimension of a subspace is the number of vectors in its set of basis vectors. So this is essentially just like a definition that we use, but so when you look at the number of linearly independent vectors needed to define our subspace, or the number of basis vectors that we have, that is essentially our dimension of our subspace. You need that when looking at the idea of rank. So the rank of a matrix is essentially the dimension of the span of its columns. So it might seem a little wordy, but that is essentially the definition of it. Yeah, I would recommend getting familiar with how to determine the dimension, and then trying to do a couple of practice problems, or just figuring out how to determine the rank. But yeah, this is like the technical way of solving for sure. Okay, cool. Okay, and then one of the last few ideas that we talked about in this class is null space. So the null space is essentially when you are doing a matrix vector operation and you are multiplying a matrix by a vector, if your vector ends up being essentially a zero vector after you do that matrix operation, or when you lose what we call dimensionality after doing that operation, that vector that you're multiplying our matrix by is essentially in that null space. So so there is a theorem associated with this idea of null space, and it's called the rank nullity theorem. So it says the dimension of the range of A is equal to the number of linearly independent columns, and the dimension of the null space of A is equal to the number of linearly dependent columns. So an equation to look at, or similar to what we looked at earlier, is when you are looking at the dimensions of the null space, it's equivalent to it says M minus the dimension of the span of A, which you might notice the dimension of the span of A is also just your rank, M minus your rank. Okay. Okay, cool. And so now that we have this idea of a trivial null space in our bucket, we can talk about what or if and only if statements, essentially, but it's essentially equivalent statements that in or with matrices. So if you know that a matrix is invertible, then you also know that AX equals B has a unique solution. So all that means is that A has a linearly independent set of columns. So we call that A is full rank. And then if that is true, we also say that A has a trivial null space. That means none of the vectors that we're multiplying our matrix by get mapped out to 0 when doing matrix operations. And the determinant of A is not 0. So that also just is another way of saying that we're not losing any dimensionality. Yeah, and these are statements that can essentially go both ways. So one statement here implies all the other statements and vice versa. Okay. Cool. And then lastly, the concept that we're going to go over are eigenvectors. So if you're applying a matrix operation on a vector, or if applying a matrix vector or matrix operation on a vector is equivalent to a scalar multiplying a vector, then that vector is in what we call the eigenbasis and is an eigenvector of matrix A. So all I'm saying here is when you're multiplying our vector by our matrix A, it's equivalent to multiplying our vector by some scalar lambda, then our matrix V is, or sorry, our vector V is a eigenvector of A. And that lambda is essentially a scalar multiple. Or sorry, lambda is actually the eigenvalue of our matrix A and associated with that eigenvector V1. So yeah, that's the high level idea of eigenvectors. So yeah. Okay, cool. So as a quick review of everything, or as of the big idea that we talked about, when we refer to a trivial null space, all that means is if you were to compute AX equals 0, and it only has a 0 solution, then we call it the null space trivial. And then on the other side of that, a non-trivial null space is when the solution to AX equals 0 is not a 0 vector. Yeah. And then another idea is when the column space loses dimension, then our null space also gains dimensionality. And then as a quick definition, the column space is the span of all columns in A, and the basis of the column space is only the set of all linearly independent columns, the minimum number of vectors, which all that means is, yeah, so the basis of the column space is essentially, in this case, all this means is if you were to take all the linearly independent columns needed to span that vector space, then the basis would be essentially the smallest number of vectors needed. So yeah. Okay, and then that last bullet point there, all it talks about is the implication statement that we were talking about earlier. So if a matrix is invertible, then you know that it has an inverse. And that implies that all of its columns are linearly independent. And that also implies that it has a trivial null space. So that's what we talked about 2 slides ago. And then it says that the opposite would be true if a matrix is not invertible. That would mean that there are some columns that are linearly dependent. So essentially not all its columns are linearly independent. And that would mean that it has a non-trivial null space. So that's what happens when you have linearly dependent columns. And essentially makes it not invertible. Okay, cool. All right, does anyone have any questions on the topics that we just talked about?
It's like my hand is raised there.
Cool.
Yeah, so for the 5 descriptions of the matrix you showed earlier, if any one of them is true, does that mean all of them are
I
true?
don't think I can see.
Just ask my hand to raise their hand, to either write in the chat or speak up.
Sure. So Mayoung, can you either unmute or put your question in the chat, please? We see that you raised your hand. We can go over the question then.
Yeah, my question was the 5 descriptions of the matrix.
Audio is on here.
Can you hear me?
Okay, cool.
Hello? Can you hear me?
I guess I can take the question in chat.
Oh, the voice is not hearable because I was trying to mute the.
Okay.
Can you hear me now?
Man.
Go
Hello?
ahead.
Can you hear me?
Or maybe
Is this hearable on the?
I don't
No, I can't hear it.
see.
Hello?
If both of us cannot hear it, then it's
Oh
a.
wait, no.
Oh.
Yeah, now we can hear you. Okay, yeah.
You can hear me now?
Yeah, sorry.
Okay, my question was for the 5 descriptions of the matrix, like the invertibility, supposed to be having a unique solution, all that. If any one of these true, all 5 are true.
Yeah, so these are essentially what I guess every single one of these implies the other one. So yes, that is true.
If any one of them is false, then all the others are also false.
Yes. Yeah.
Okay, thank you.
It's invertible, the first one, it needs to be square.
It needs to be square as well. Oh yes, that is a really good point. So something to note here is when your matrix A is invertible, it also has to be a square matrix. So that's something else that you can add on there. Yeah. But yes, thank you so much for clarifying. Okay, cool. Okay. So now we're going to do a couple final review questions. Or these are just like questions from past midterms that go over some of the concepts that we talked about. This problem's a little long, so let's take 10-ish minutes to go over the problem and then maybe try getting a solution for each of these, and then we can talk about it. Okay, sure. Sounds good. So maybe 5 minutes, and then no worries if you don't get to everything, we can talk about the solution together.
Well, I'm going to check if the sound is actually working, because this is slightly. Okay, there's a lot of chat messages. Okay, somewhere around here. Yeah, it is probably okay. I feel like this should be working. Let me go back to posting this.
Nicola, I really want you to repeat what you were saying about null space and loss dimensionality.
Okay. Or should I do it?
Oh yeah, you can do it. They're asking you to repeat what you said about the vector zero with regards to the null space.
Sounds good. Yeah. Okay, cool. So I was just told that we wanted to go over what I meant by the null space and vector zero. So all I meant there is when you do a matrix vector operation, or when you're doing a matrix operation on a vector, and it essentially maps to the zero vector, or you essentially lose dimensionality on that vector, then you can say that that vector is a part of our null space. And that's essentially just the idea behind a null space. I think so so when you're solving for the null space, that's all you're doing. You're trying to find all the vectors that lose dimensionality when you're applying a matrix operation on that vector. And that's all I meant by that. Okay, cool. So let's start to go over the answers to these questions. So our first question here is asks us or to define or to go through each of these statements and tell us if they are true or false. So for part A, it says there exists an invertible n by n matrix A for which A squared equals 0. And the solution to this question is false. And the reason why is to see it, at least in a visual way, you start by just looking at the case where you have an n by n invertible matrix. So when you multiply both sides of our equation, A squared equals 0 by A inverse, then on your left side, you have, you can essentially group like terms. So you can split up your A squared into A times A. Then you group A inverse times A. And then on the other side, you group A and A inverse. And that essentially gives you two identity matrices. And then when you multiply them, you end up just getting one identity matrix. So that is the case where you have just an invertible n by n. However, if you have the case for which A squared equals 0, then very similarly, you can do your you can essentially split up your A into A and or A and A, and then left multiply by A inverse. But in this case, you don't get the identity matrix. And so you essentially end up with an equation that looks like A inverse times A squared times A inverse equals 0. And your 0 is essentially just a matrix of all zeros. So you have a contradiction where you don't end up getting the same thing on both sides. So yeah, that's the explanation for this question. And our part A is false. Okay, part B. It says, if A is an invertible n by n matrix, then for all vectors B that are in the R of n space, then the system AX equals B has a unique solution. So this was one of those equality or equivalent statements that we looked at earlier. But we could say that if our that this statement here is true. So if our A is invertible, then we have a unique matrix, A inverse. So that is the definition of an invertible matrix. And then you can left multiply our equation by A inverse. And so you end up getting X equals A inverse times B, where our X is a unique vector. So so you can essentially say it's true based off of those equivalent statements that we pulled up earlier, but this is a way of showing it with a proper justification. Okay, cool. So for part C, it says if A and B are invertible n by n matrices, then the product AB is invertible. And this is true. And the way to do that is if you have, for example, a matrix AB that is invertible. This is a property that maybe should be written down on cheat sheets, but if your A times B is invertible, that is, or if you get the invertible matrix of A times B, that's equal to your B inverse times your A inverse. And they kind of show you how it works for if you're looking at the product of AB being invertible. So when you multiply your AB times your AB inverse, it turns into AB times B inverse times A inverse. And then you can see, like, by grouping terms, you get B and B inverse as an identity and A inverse as an identity. And so that just ends up giving you the identity matrix. And when you multiply two matrices together and you get the identity matrix, that means one matrix is the inverse of the other. So that essentially shows us the solution here, and it is true. Okay, cool. And so for part D, it says the two vectors v1 equals 1, 1, 0 and v2 equals 1, negative 1, 0 form a basis for the subspace 1, 0, 0 and 0, 1, 0. Or essentially the span of those two vectors. And our solution to this is true. So one way to look at this is if you were to essentially these, in order to determine the span of two vectors, you just need to look at whether or not they're linearly independent and what space they could span. So in this case, the span of 1, 0, 0 and 0, 1, 0 essentially spans the XY plane. So if you essentially don't look at that Z coordinate, then you have 1, 0 and 0, 1, and those are unit vectors on the X and Y axis. And so that essentially spans the XY plane in R3, and then adding in that 0 just says that it's spanning that base plane. And then since our V1 and our V2 are linearly independent, we know that they also form a similar basis in for the XY plane. The way you can determine that is you can manipulate both V1 and V2 or find linear combinations of V1 and V2 that equal to these basis vectors. So yeah. Okay. And then for part E, it says the set of n linearly dependent vectors in R of n can span R of n. So as we talked about this idea earlier, but in order to find a set of vectors that span R of n, you need to find a set of linearly independent vectors that span R of n. So this isn't entirely true. If you have a set of linearly dependent vectors, then you don't have enough information to write out all the vectors that span that space. So a set of n linearly dependent vectors can span some subspace of dimension 0, which is less, or can be between either dimension 0 or n in R of n, but cannot be equal to the number of vectors in R of n. So yeah, that is, and in the note here, it says it's incorrect to say the set of linearly dependent vectors spans R of n minus 1 for 2 reasons. First, you do not know what the dimension is of the subspace it spans, and it could be less than n minus 1, so you cannot say that. And then second, there's no such thing as R of n minus 1 belongs to R of n. So the vectors are in R of n based on how many elements are in the vector, and a set of vectors spans some subspace, potentially the entire space. So you can't entirely say what space it spans, because it could be essentially less than n minus 1. In this case, that's what that note is saying there. Yeah.
Go back over it and see, I think, what the key are.
Yeah. Okay, so for A, it says there is an invertible matrix n by n matrix A for which A squared equals 0. So all they did in this explanation here is they left multiplied our matrix by A inverse, and then they saw that in that A inverse would usually equal the identity matrix. But if you were to essentially break down the identity matrix into like A inverse times A and then A times A inverse, then it also equals like this product here, A inverse times A squared times A inverse. And in this question, it says that there should be an invertible matrix that equals 0, but the 0 matrix isn't equivalent to that identity matrix. So you can't entirely say that this is true. And that's where the contradiction comes about, essentially. Yeah. And then for part C, all they're doing here is they're using this like very basic notation, or sorry, this basic operation that says that, or formula per se, that says that A, if you're taking the inverse of A times B, then that's equivalent to B inverse times A inverse. And they're plugging, and we know that the definition of an inverse is when you take a matrix and multiply it by essentially the inverse matrix to get the identity matrix. So using that property, if you multiply it AB times AB inverse, it would equal the identity matrix. And then the AB inverse can be replaced by that formula above, so B inverse times A inverse. So plugging that in, grouping like terms, you end up getting the identity matrix. So So this basically tells us that our product AB is invertible. Yeah. Yeah, that is about it. And the place where AB being invertible comes into play is when you're grouping like terms in our AB times B inverse times A inverse form. You can essentially say B times B inverse is equal to the identity matrix and A times A inverse is equal to the identity matrix. So that essentially breaks down that formula that we have up earlier. Okay, cool. Okay, the last question here was for all matrices A and B, where A is a 5x5 matrix and B is a 4x4, it is always the case that the rank of A is greater than the rank of B. So the solution to this question was false. So it says that the size does not determine the rank. So for example, if A was a matrix of all ones, rank A would just be 1. If, on the other hand, B was identity matrix, then it would have full rank. So rank B would be 4. So essentially what they're doing here is they're saying that it is false and that the size does not determine the rank, but they're using they're giving a example of a situation where rank A is greater than B would not hold. And this is like something that you can use for proofs a lot of times, where if you can show that there's one situation where one of these operations don't, or where the statement that we're trying to prove does not hold true, then you have proven that the entire statement is false. So it says you can only claim larger size implies larger rank if you assume that the matrices are full rank. And once again, the definition of full rank is that when you're in reduced or echelon form, there are pivots in every column, and all the column vectors are linearly independent from the rest of the vectors. So yeah, that is about it for this problem. Okay, so we're going to move on to our next problem, which has to do with looking at augmented matrices and figuring out how many solutions they have. I'm going to give everyone a minute to just read the question and see, and then I'll go over the solution to it. Okay, cool. So it says let the following matrix A, which they have shown here, be an augmented matrix that corresponds to a system of 4 linear equations in 3 unknowns. How many solutions does the system of equations have? So for this question, the way to go about it is to look at what each of these rows tells us. So you'll see that in this form, our row 2 and our row 4 are almost entirely equivalent. You'll see that there's a star on our third column for both row 1 and row 2, but it says that the solution to these equations for one of them is 0 on row 2, and for the second one it is another star. So all that means is that our x3, or our third variable, is it's saying here that it is equal to 0 and it's equal to some value, some real value, which is essentially a contradiction. So this is a no solutions, because it says the second row of matrix A gives x3 equals 0, while the fourth one gives x3 is not equal to 0. Hence, the system of equations is inconsistent. Okay, and for the purpose of time, I'm just going to go over the solution to this and walk through it. But it says, so we have our following matrix be a system of 4 linear equations and 3 unknowns. Select all that apply. So our first option is the 4x3 matrix corresponding to the original system of equations has a non-trivial null space. We can say that, so it has a non-trivial null space. We can say that B is in our reduced row echelon form. We can say that B is also in row echelon form, or that B corresponds to a consistent set of linear equations. So the solution to this question is that the matrix is in row echelon form. We can tell that our matrix cannot be put in reduced row echelon form, as the pivots are not known to be ones. So all that means is when we know that when we're in reduced row echelon form, our pivots or the values in our diagonal are equal to 1. And we can't entirely say that because we know them as stars as of now. So the system of linear equations is not consistent because the last row says when all our variable or scalars for our variables are 0, it equals to some scalar, which isn't a true equation. And then the matrix, the left of our separator, has linearly independent columns. So therefore can only have 0, 0, 0 transpose as the null space. So so the bigger thing to note here is we can essentially rule out every single A, B, and D. And we can tell that our B is in row echelon form, but not reduced row echelon form, because we do not know what those pivot values are right now. Okay, cool. And then I'm going to go over C and then hand it off for module 3 or module 2. But so we're going to first look at this matrix C here. Let it be an augmented matrix that corresponds to a system of 4 linear equations and 4 unknowns. Which statements are guaranteed to be true? So we have a couple questions on how many basic and free variables are in this system of equations. And note that as a definition, a basic variable is essentially a pivot variable, or a variable that isn't free. So something that has a 1 when we go into reduced row echelon form. And the solution to this question is E, that the system is consistent. So we can say that since both are elements of, I guess when they say C, it's C2, so on column 2 or row 2, column 5, and row 3, column 5 are 0, the matrix can be brought into reduced row echelon form without having a line that will be equal to 0, 0, 0 equals 1. So that's something that we saw earlier. We had 0, 0, 0 equals some sort of scalar. So we know that the system is what we call consistent because of that. But we can't deduce anything entirely about the number of free and basic variables because we don't have it in a form where we can determine that. So that essentially depends on whether or not our rows 2 and 3 are linearly independent. So this one might take a couple minutes to soak in, but because we don't entirely know what the values are for those stars, we can't exactly jump to conclusions on how many free and basic variables we'll have in this. But yeah, that's about it for module 1, and I'm gonna hand it off for module 3 now. Yeah.
Skip a few slides ahead.
Yeah. All right, feel free to go over those in your own time. I think those are like good questions. But now we're going to talk about module 3, which is the latest material you've learned. So, sorry. Yeah, so we covered like linear algebra stuff, and module 3 is a lot about like the applications of linear algebra, which is really neat. First off, we're going to talk about inner products. So let's talk about what inner products are. So inner products are any operation on 2 vectors that satisfy these properties. So the first one is symmetry, which means you can flip them around and the result stays the same. Then we have linearity, which is very similar to what you've done in the past with functions. This first one is you can pull out the scalar and it ends up being the same. And the second one is you can add, you can basically distribute an inner product. And then finally, we have positive definiteness, which states that if we take an inner product of a vector with itself, it's always going to be non-negative, and it's only going to be 0 when the vector is 0. So yeah. Now that's like kind of the general like inner product, but really in this class we focus on a specific type of inner product, the Euclidean inner product or the dot product. And this is defined as X transpose Y. Essentially, you're going to pairwise multiply each of the like corresponding elements in the two vectors and then add them all up. That's what this operation does. Alternatively, another way of writing this is equal to the norm of X, which is like the length of the vector, times the norm of Y, times cosine of the angle in between them. So both of these ways can be useful like formulas for the dot product, and you want to use them in different applications. So what's like the intuition behind dot product? Well, essentially it measures the similarity between two vectors. The reason behind this is that we look at this formula here and we see this cosine theta term. So cosine theta is maximized when two vectors point in the same direction. That's because when two vectors are pointing in the same direction, the angle between them is 0 and cosine theta is the highest it can be. And if they're opposite directions where the angle is like 180 degrees, then cosine theta is going to be -1, which is the lowest it can be. So the more similar the two vectors are, the higher the dot product. And then we also have this other useful property with dot product where the squared norm or the length of a vector is the dot product of the vector with itself. So it's a good idea, like if you have a problem with norms and stuff, to try to make those into dot product form, because you can, when you make it in dot product form, you can like take advantage of these properties. We'll see an example of doing that later. But yeah. Any questions on this stuff? So inner product and specifically dot product. Well, okay. Yeah. And I also wanted to mention that this property here, the squared norm of the vector equals the dot product. That's why the dot product, or that's like one way to see the application of this positive definiteness property. The reason being is that the length of a vector always has to be non-negative. It doesn't make sense to have a negative length. And the only way you're going to have a 0 length is if your vector is 0. Okay. Then a quick note about what it means for two vectors to be orthogonal. I think you've like briefly skimmed this, so it might show up, but vectors x and y are orthogonal if their dot product equals 0. And this, another way of thinking about it is it occurs when x and y are perpendicular. The reason being is that cosine theta is 0 when you have when you're perpendicular. So now let's talk about another concept that you've learned called cross-correlation. So cross-correlation is a technique that basically helps us find where in our received data, which could be like a jumble of a lot of different signals, a certain signal would most likely be. So if you're thinking about in the context of GPS, right, you're going to be getting signals from a whole bunch of satellites. How do you figure out where the location or where in your data the signal from satellite 1 is, or the signal from satellite 2 is? So basically, when we're calculating the correlation between x and y, as you can see here, we are going to look at the sum of all the elements of x and y, but y is going to be shifted a certain k amount. This is equivalent to saying we're calculating the dot product of x and y, but y is shifted by k. So basically, we're going to shift y by different values of k, and then compute the dot product of each of those values for k, and then see which dot product results in the highest value. So the core idea here is that, as I said before, dot product measures similarity. So the highest correlation is like the highest dot product, and that gives us where the signals are most similar, which is why this can tell us where you can find a certain signal within your received jumble of data. Okay, so let's like go through an example, because I remember when I was first learning this, I was like, these formulas look really confusing and all. But let's look at these ones. So let's say 1, -1, 2, and 3 is our data, and 2, -1 is the signal we're trying to find. So what we can do is, let's look at the second entry first. So we have 1, -1, 2, 3, 2, -1, 0, 0. We align 2, -1 with the beginning of the received data, and then fill the rest with zeros, just as the default. And then we compute the dot product. So we see 1 times 2 gives us 2, -1 times -1 gives us 1, 2 times 0, 0, 3 times 0, 0. And we add them up, and that gives us 3. Then on the next one, we're going to shift that. So you see the 2 gets shifted by one place, the -1 gets shifted by one place, and then we pad it with zeros. So we compute the dot product again, and we go 1 times 0, 0, -1 times 2 is -2, 2 times -1 is -2, and 3 times 0 is 0. And in this way, we can keep computing the dot products and see which one is highest. You'll notice on like the left side, there is no 2, so that basically just ends up being like, because it's out of range of the 1, -1, 2, and 3. Yeah.
For cross correlation, if it's like an absolute value of magnitude, so it's like in this case you have -4, you also have 3. Would it be -4 because 4 is larger than 3, or would it be 3 because 3 is larger than -4?
I think generally it's just, correct me if I'm wrong, but I think it's just you don't take the absolute value for cross correlation. All right. Yeah. Because if it's negative, that means they're like really different, the two vectors. Yeah, good question. Okay. Any other questions? There's also variants of this, like circular and periodic cross correlation. You can like take a look at the note. They're the similar ideas, just slight variations. But here's an example cross correlation plot, where on the bottom side we have like the values of k, our shifts, and on the y-axis is like the dot products, the correlation values. So we're basically looking for the peak. So according to this plot, it's most likely that our signal was received around like 180, something like that. Yeah. So now that you use cross correlation, that helps you compute the time delay of your signal. So how long does it take for your signal to reach from the satellite to you? You can multiply by the speed of the signal. So that could be speed of sound, speed of like light, whatever it could be, to find the distance to the source. And then once we know the distance to our sources, which like in GPS, it's the distance to the satellites, we can use trilateration to find our location. So I'm going to talk a little bit about how to do that. So there's a lot of math behind trilateration, and so I'm just going to go through that, but then we're going to have a chance to practice some problems afterwards. But the idea behind trilateration, as I said before, is like we often like dot products better than norms. So we want to make our norms into dot products because those have nice properties of linearity that we can exploit. So on the first line, this is basically kind of a definition. So this is saying X is like your location, and SI is like the location of satellite I, and DI is a distance from you to satellite I. So what this is saying is that the vector in between X and SI, if we take the length of that, that equals the distance. Does that make sense to everyone? Okay. These trilateration problems, I often like to just start from the basics, even when on an exam. So I like to write down this. From there, I'm going to square both sides. And then once I have a squared norm on the left side, I can break that out down into a dot product. And then from here, I can actually use distributive property and end up getting the fourth line. So from there, we get quadratic terms with x squared. And we don't really like quadratic terms. In this class, we focused a lot of our attention on linear equations. So we want to get it into linear forms. So the way we can do that is we can actually subtract our equations from each other to get rid of the quadratic term, because all of them will share this norm of x squared. And then when we actually do that, we can subtract like equation 1 and 2, equation 1 and 3, equation 1 and 4, and you end up getting n-1 linear equations. So if you started out with n equations, where you have n satellites, you have n equations, you end up getting n-1. So that means that to solve for your a-dimensional position, let's say you want your 2D position, you need that n-1 equals a, because you need as many linear equations as you have unknowns, which means n has to equal a plus 1. Does that idea make sense to everyone? How are we feeling about that? Yeah. Cool. So sometimes we might need to add another unknown variable. So one example in this class was if the receiver isn't like the clocks aren't synchronized with the source, then we might need to add another unknown for like the time difference between those. So for that, all you would need to do is have another linear equation, which would mean you would have another satellite. So I think the core idea here is like number of linear equations equals number of unknowns. And because we had to do this subtraction, we actually need one more. Okay. This is just a fun little meme. Okay, so now we're gonna go through like a trilateration problem. So let's see, are you all able to read that on the screen? Yeah, cool. Yeah, I'll give everyone like 1 minute to work on this one. This one doesn't need any trilateration or cross correlation, it's just conceptual. Let's go over this one real quick. So the idea here is that T is our transmitter or like the satellite, and R1 and R2 are like, you know, your phones using GPS. It's like I always like to think of everything in terms of GPS because that's like what you've learned. But if we send it out T starting at 0 milliseconds, the signal starts at 0 milliseconds, then R1 receives it at 9 milliseconds. So that tells you that it took 9 milliseconds for the signal to come to R1. And if the speed of sound is 300 meters per second, then I think if you do the calculations, let's see, you end up getting 2.7 meters. And then similarly for the left one, sorry, not the left one, for the second one, R2, we see that the signal is received at 11 seconds or milliseconds. So we just multiply again, 300 meters per second by 11 milliseconds, and we end up getting 3.3 meters. So normally you would use cross correlation to solve this, but they told you in the problem, like they kind of already filtered it out for you to show you exactly where the signal was. From there, once you know the once you know the distances, you can solve for the location using trilateration. So this is the trilateration problem. So I'll give everyone like, let's say 5 minutes to work on this one, I think. Yeah. For this one, if you're like feeling a little stuck, remember you don't have to solve it like the vector way. You can do it like how you learned in algebra, like do this equations for circles. It ends up being the same thing. It's just vectors are like often a more compact way to represent it for higher dimensions. But since this is only 2 dimensions, I think either way is a great way to solve it. Okay, in the interest of time, let's go over this now. So, I guess I'll just give like a quick overview of the solution, and then you can like go back later on and check the slides since I don't want to spend too long on it. But over here is where we can write our equations. So notice in the solutions, they've just written it in terms of x and y. Writing it with vector form is equivalent. So again, as I said before, vectors are just like a more compact way, but since this is just 2-dimensional, you can do it with just x and y. So for example, for the first one, we have x squared plus y minus 4 squared equals 1. So what this is saying is that you can see for the first one, we go from 0 to 4, and then d1 equals 1 meter. So it's like a circle centered at 0, 4, and the radius is 1 meter. So x squared plus y minus 4 squared equals 1. This is the same thing as saying that our vector minus 0, 4, the norm of that squared equals 1. Okay. And then from there, once we get all our equations, we end up subtracting them to give us 3 linear equations. And when we write it in terms of a matrix vector form, we see we end up getting this kind of system where we have this column of zeros. So this should tell you, like, at first glance, like, oh, something's off, something's weird. And you might think, oh, it's like linearly dependent columns because we got a column of zeros. And if you were actually to solve it out, you would see that y has to be 4, but x could be anything. So what this means is that like there are multiple solutions to the system. There might not be infinite solutions because when you plug in 4, y equals 4 into your original equations, you would get like 2 values for x, plus 1 and minus 1, but there's like more than one solution. So because there's more than one solution, we can't definitively say where we are. And the reason behind this is that the way we place the microphones made the columns of the matrix linearly dependent. So we can see here, all the microphones were placed where x equals 0. So they're all like actually like multiples of each other. 0, 4, it just equals 2 times 0, 2. And thus if we place the microphones in a different way, then our problem could be solvable. I'll let that like Give you all like a couple seconds to let that sink in, but any questions on that idea? Any questions in the chat that I can answer?
We are allowed to use circle questions and third combination. Can you basically explain why we can use the circle equations for that?
Why we can use circle equations?
Like, do we know trilateration if the circle ones work every time?
Oh, do we need to know?
Trilateration. Oh, do we need to know? Okay, I think we should clarify what trilateration is. Like, we're still doing trilateration.
Yeah.
But like the vector is one way of doing trilateration.
Yeah, so when we're using these circle equations, they're basically just a different way of writing like our vector form. So they're both ways of accomplishing the same task, which is trilateration, using like different like satellites or whatever our like beacons are to figure out our location. But they're at the core, like they're just like a different way of writing it. So literally if you took like x squared plus y minus 4 squared, I don't know. Is there something I can
It's touchscreen, right?
This is a touch screen. Let me get my pad real quick.
okay, I can connect to my iPad.
Okay.
So I just asked the question. Okay.
I have a pen, but the way this tablet works, I'm right.
Yeah, but just to answer your question real quick, I don't think we can say exactly what you need to know and don't need to know. But I would say if you're more comfortable using the circle equations, that is definitely a perfectly valid approach which you can use. That's my viewpoint on this. Yeah,
helpful. Thank you.
I need to like do this when you write because the new laptop is out, so it's specialized in writing.
Yeah. Okay, so let's like look at x squared plus y minus 4 squared equals 1 and see how that's like equivalent to writing it in the vector form. So in the vector, I think our P1 was.
Did it show up?
Is it showing up? No.
Do you want me to try it?
Yeah.
Okay, so. Yeah, just need to do it harder.
That's the word.
Is this pen only listening to me? Okay, I'll write for you then. Okay, so
You can say like P1. So if we have like P1 equals 0, 4. And then from there, we can say that our location is like, let our location vector be like, I don't know, L. So we can say like L minus P1. And then the norm of that squared equals the distance squared. Yeah, so L1 minus 0 and then L2 minus 4,
which is equal to. Let's see here.
Yeah. So those are essentially like at the core, they're the same thing. It's just a different way of writing it. I think if they gave you like a 5-dimensional thing, you know, it'd be easier to do in vector form. Thanks.
I did not know my pen only listens. I learned something new today.
Okay. How much time? Okay, I think I'll skip this problem, which is another like trilateration one. So yeah, I'll let you practice this on your own, but actually first, any questions on this? Any more questions about like the vector idea that I just talked about? Yeah.
to get a setup that works, you just need to move one of the vectors so that there's like an X that's non-zero.
Yeah, as long as. Yeah, because you should just not have this like column of zeros because it makes a linear independence. Yeah, good question.
And so when we do cross correlation, just in the notation where it's like 4 and then X and then in parentheses Y, Y is the vector that we're shifting by k, right?
Yeah.
It's like a convention thing. It's like not a question.
I think the answer, whether you shift X and or Y, ends up being the same.
It'll be flipped around. It'll be like backwards.
Or like negative.
Yeah.
Yeah.
So it'll be like the order will be reversed. So it's important that you know which way around it is because you don't want to get the answer reversed. But it's like a convention thing. There's no specific reason why.
I'm going to write this off the whiteboard just for quick.
They can't see the whiteboard though.
Yeah, no, it's
Got to it. So used to this. Okay, so I'll probably explain this later, I guess. But the main way it works out is like this.
Oh, like this?
Yeah.
Like how it's just to
Yeah,
shift
because
to negative.
this was what was written on the size word, and then this is just from the iPad on the before.
I think we can, yeah, so you can see the negative sign swap to the positive. I think we can allow it over this now. If you want to write on the board for the benefit of people here, you can do that.
Okay, actually, we can do that in the middle.
Yeah. Okay, so let's just move on to least squares now, because I think that's like, in my opinion, the biggest topic for module 3, something you should like be comfortable with. So first, to understand least squares, we first need to think about the concept of projections. So projection asks or answers the question, how much of a vector lies in a direction? So lies in the direction of another vector or on a plane formed by 2 vectors or something like that. So if we first start with vector onto vector, we use this formula. So it's the dot product of A and B over the norm of B squared times the vector B. So it's like a pretty complicated formula. But the way I like to remember it is I don't think the norm of B squared, I think like B dot B. So I would go A dot B over B dot B times B. But yeah, you'll have a cheat sheet, so write this formula down. In the interest of time, we won't go over a derivation of this, but instead we'll go over a derivation of least squares, which is closely related to projections. Yeah.
Good exercise is to use the least squared formula to derive the projection. It's actually the same thing.
Yeah.
Yeah. Good.
So least squares is essentially the projection of a vector onto a plane or a column space. So let's talk about, I guess first, the motivation behind least squares. It's used to kind of estimate a solution to a system of equations. So that's very helpful. Say we have some like noise coming in from external sources, and therefore we don't have a single solution to our system. Least squares helps us find like a solution that basically minimizes the error from all like the constraints. So the way we think about this is, let's say our system is supposed to obey AX is B, but it's not exactly obeying it. It's more of obeying AX equals, or AX plus some error term equals B. So in this case, this diagram basically illustrates that. So we have some matrix A, and the column space is this plane over here. And A1 and A2 are the columns. So the span of those form the column space of A. And then we have this B. So note that B is kind of coming up because B does not lie within the column space of A. If B was within the column space of A, that means we could find an X that works like perfectly. But because B is not within the column space, there was some like error, and that's the whole reason we need to use least squares in the first place. So we have this B coming up here, and then we have this A X hat. X hat is basically our predicted value for X after least squares. So that's going to be coming down from here, and then we have an error term in between these. So that represents the difference between our actual result and then our predicted result. Okay, any questions on that kind of setup before I go more into how to derive something from here? No? Okay. Now the core idea here is that it ends up being the case that our what they call P here, or AX hat, and our error term are perpendicular. The reason behind this is, imagine if we had another AX hat. So imagine if we had, let's see if I can get this right this time. Ah, I got it. Okay, let's say we had another one that came here, and then the error term. Okay. And then this would be our error term here. Notice that that error term is a lot longer. So in least squares, our goal is to minimize error. And if you remember from geometry, the minimum distance is the perpendicular distance, right? So that's kind of the same intuition. When we end up being perpendicular here, that ends up being the closest we can get. That's like the minimum distance to B. So by having it be perpendicular, we're minimizing the norm of E, which is the goal in least squares. So if they are perpendicular, we know they must satisfy this because they're orthogonal. So A transpose E equals 0. From there, we can rewrite E as B minus A x hat. Sorry, I couldn't do the x hats in slides. It wasn't letting me, but imagine there's like x hats here. Okay. Okay. Anyways, so we have A transpose B minus A transpose AX hat equals 0. From there, we can move around terms, and we end up getting this magic formula for least squares: X hat equals A transpose A inverse A transpose B. Yeah, just something to definitely write down on your cheat sheet, this formula.
It's gonna be my first body tattoo.
Isn't there a picture of like Anna, I think, with like
Yeah, there was.
a tattoo? Yeah. Any questions on this? None. Let's move on to some practice problem. So, yeah, I'll give everyone like, let's say 5 minutes to work on this one. I think it's good practice because this is often like the format like the exam problems take, where they give you a situation and you need to find like model it using least squares. So I think first focus on like formulating a least squares problem, which means like defining what the A, the X, and the B are in your system. And then the last step is to actually do the numerical calculations, which in my opinion are not as important as figuring out the conceptual part. And then if since it's difficult to see, you can pull up the slides also. They're linked on the ed post. in the interest of time, I'm just gonna go over this now, since we should get to like module 2 stuff soon. But the idea here is we first want to formulate our problem. So we notice our system, we like model it as S is approximately equal to KV. So in this case, K is what we're trying to solve for or use least squares on. So K is going to be like our X, and our predicted K would be our X hat. V is going to be our A, and X is going to be our B. So when we write it like this, it might become clearer. We get 4, 10, 15, which are coming from our V's. K equals 1, 2, 3, and 1, 2, 3s are coming from our position S. So it's just plugging that in and rewriting it in kind of the form used to. And then from there, we can plug in our A and B vectors and get that answer. The next one I'm just going to talk about. So in part B, we're going to be using a different model to represent our system, which is S is approximately equal to KV plus B. So notice that least squares, they're dependent on the models we choose. So we can like define how we want to model a system and then fit our data into that like into a formulation of the least squares problem according to our model. So here we're going to do S is approximately equal to KV plus B because we think that maybe there's some shifts. The way we can solve for this is notice that, I guess, this is equivalent to saying, oh,
Yeah, present.
I can just write it with my mouse, I think. There's not much.
Yeah, try.
Okay, let's say K.
Here's another one that's easier for writing, but it's battery drains in an hour.
Makes sense.
This is why we need to learn.
This is equivalent to saying KV plus B times 1. I think that's a good way of thinking about this. Because K and B are your unknowns and V and 1 are your knowns. So when we end up writing it in terms of like what we want with KB as the vector of unknowns, you'd end up getting a matrix with V's and 1s because those are your nodes. So more concretely, it would look like this, where you have -3, 4, 10, 15 as our V's column, and then 1, 1, 1, 1 as our coefficients for our B term. So if you think about like the first line of this, it would look something like -3K plus B equals 0. The next line would look like 4B plus K equals 1. The good thing about writing it in matrix vector form is now we can just apply our least squares formula. Okay. Any questions on least squares? Just as a final note, kind of the paradigm we're following in least squares is a little different. In past, like when you're normally solving a system, you kind of know the parameters of your system and you're solving for kind of the values. But in least squares, you know the values of like different quantities, but you're solving for parameters. There's an extra challenge if you want to work on that. And now module 2.
And then I'll take over. So once again, thank you for your good use of time during this rainy afternoon to come listen about circuits. So now we're going to review module 2 for a bit. And on there, you can see a link of today's material for module 2 review, where you'll see a Google Drive folder. So if you would like to try to type the tinyurl.com link into your computer, you can see the module 2 worksheet for today, which we're not going to go through everything for. And I'll also be pasting this link directly on chat. All right, so now that this is posted on the chat, I am going to change the entire screen share to the entire screen so I can write on my notebook later as well. All right, so I would like to talk about why we should learn about circuits, but I think that's evident enough because today's Zoom has a bit of a sound issue. So disclaimers, we cannot go through everything in module 2 within 45 minutes, but in exchange, I'll be listing a bunch of review resources at the end of the slide. And in return, we'll be going through the listed topics on the slide for today. While we will not go through these topics, which I would like to talk about first, and the topics we'll not go through are resistive touchscreen, capacitive touchscreen, and negative feedback amplifier structures, which you might see plenty of design problems on, but we'll talk about that later a little bit as well. So first of all, let's try to define circuits. Circuits themselves are, in fact, essentially combinations of different circuit components that can do different things for you. So here are some of the, oh no, not again. Your internet connection is unstable. All right, is there any sound now? Is there any sound coming out? Okay, it might be our edge room. Is it, wait, how do I know if I have any sound on Zoom?
So I heard myself coming through the thing.
Let's see if the microphone's going. Hello. I see the microphone's going out, but
They can hear you.
oh, okay, thank you.
The fact that I got feedback means that's why I unmuted myself.
Yes, feedback.
Now I'm-
All right, we'll talk about feedback a little bit more. As well.
Yes, there should be positive feedback. Oh.
Okay, once again, disclaimer, and first of all, module 2, here's the link for today's resources. It's in the Zoom chat. Disclaimer, we'll not be going over everything in 45 minutes because that's going to be way worse than a speed run. But in return, once again, we'll be going through the following topics. We'll not be going through touchscreen and negative feedback amplifier structure, but we will be talking about negative feedback. Okay, so once again, what is circuit? Circuits are essentially a combination of electric components that do things, and this do thing is very customizable. But here are a few characters of circuit components I would like to use in 16A. First of all, we have the voltage source, which offers voltage equivalent to V volts to the circuit. And it is very important to note that the voltage is supplied on the positive side, not the negative side. And you flow in the wire from the positive all the way across the circle to the negative. Oh no.
You could use an adapter. Yeah. I mean.
Oh, okay, yeah.
42%. So.
The microphone might work, I guess. If we just use your microphone and then I'll just use it.
You mute yourself.
Okay, yeah, that works out. All right. So am I once again audible? Probably is. Okay.
Yes. Okay, cool.
All right, nice. All right. So once again, voltage source is a source of voltage where it offers voltage equivalent to V volts on the circuit as labeled on your diagram. And it is very important, once again, to note that the voltage of a voltage source is supplied from the positive side of the source. And the voltage goes way across the circle to the negative side. I, for some reason, made a lot of that mistake, so I like to notice that as well. Meanwhile, here are also resistors, which are components that prevent or resist current. And for a resistor with some constant resistance, we can see a famous equation called the Ohm law, where the voltage across your resistor is equal to the current across your resistor times the resistance itself. Meanwhile, we are not just stuck at using voltage sources because there's also current sources, which is just a current version of the voltage source. It offers current equivalent to the labeled quantity and the direction of the arrow mark on source. So it is also possible that your current source gets labeled with a negative current. In that case, you'll just supply a negative current along the arrow mark direction. Meanwhile, we see more resistors, but you also see that resistors can be combined in networks that are as confusing as possible. However, there are also ways to simplify those kind of resistive networks, which we'll talk about before. But for now, let's talk about an important part of analyzing circuit, which is nodes. Nodes are basically space between circuit elements. And nodes are directly connected, and we can see that nodes are directly connected to different electric components depending on what components are these nodes in between. Note that within any space of one same node, they'll all have the same electric potential, which means that the voltage you see here and here are the same because they're within the same node. So on this circuit, we can see 3 nodes. One of them is connected directly to the positive side of the voltage source, meaning that they'll have the exact same amount of voltage that the voltage source provides. Meanwhile, there's also a node that is connected to the negative side of the voltage source, where all the electric potential are gone. Here's where we put a ground symbol here and speak of this as a ground node. Last but not least, here's also a node between the 2 resistors, which is the node that we're going to try to derive the voltage for. It is very important and very useful to know how to derive voltages between different nodes, and we'll give an example on how to do it. So here's the entire process of node voltage analysis in a nutshell. First, we would like to label nodes, which is for our own sanity and your greater sanity, so that we know which node we're referring to in the analysis. And we'll also like to annotate the circuit with passive sign notation, which means your current flows from positive to negative, and you also label the different currents across different resistors. This is also very important because you'd like to keep some sanity between calculations by having a uniform system of variables to track through. So as we have labeled the nodes, we can now start listing facts about the circuit in mathematical expression. And later we'll just piece a lot of these equations together into one single equation. So here are some of your friends in try to listing facts in mathematical expression. One of them is called the Kirchhoff's current law, which states that the current that goes into one node is equivalent to the current that goes out of one node. So for example, the current that goes into U2 is equal to the current that goes out of U2, which would allow us to say that the current across resistor 1 is actually equal to the current across resistor 2. Meanwhile, there's also the Kirchhoff voltage law, which states that the sum of the voltage in a loop is equal to 0. And in this case, what it means is that, we'll actually talk about this in the next slide, is that considering the voltage supplied as positive and the voltage depleted or voltage across resistor, which you use up as negative, if you add up these voltages together, it should sum to 0. So in this case, we can see the KCO and KVO results, where the KCO is as we talked about before, but here not only are we listing it as IR1 or IR2, we also like to list it as a fraction of node voltage difference and resistor, because it's easier for us to look at the equation in terms of node voltage than in terms of current, where we still have to derive a lot of different things. Meanwhile, for KVO, we can see that the voltage supply is indeed equal to the voltage depleted by the circuit. So afterwards, we can then assemble all of these different formulas together and try to derive for the voltage at U2, which, as you see, follows this long LaTeX derivation that we don't have time to go through. So please go through this in your own time if you'd like to. But that being said, this is the basics of node voltage analysis, which will be a fundamental skill for you to look throughout the 16-year finals. That being said, now let's talk about one of the big elephants in the 16-year room, which is Thevenin and Norton. First of all, why would we like to use equivalent circuits when they're so confusing? And the reason why we like to use this structure is actually because it makes things less confusing. If you think back to the original current circuit example, where we have a network of 4 resistors and one current source, it becomes very confusing for us to try to figure out or simplify calculations in terms of how the circuit will work out. So what we like to do in this case is to then perform equivalent circuits that have the same IV relation by simplifying a circuit down to one of the 2 models below, which one of them is called Thevenin, uses a voltage source and a resistor. The other one's called the Norton model, which uses the current source and a resistor. To find the Thevenin voltage of a circuit, let's draw a circuit here actually, just to make some sense out of this. So say that I have a very complicated circuit, which we'll talk about. This is the exact circuit in the practice problem. Where say I have this circuit and I have terminal A and B, which should correspond to the terminals A and B in the different models of the circuit. This circuit itself is quite complex. Actually, let's make it even more confusing by adding a resistor here. So once again, the value that comes in simplifying this circuit is that you can then simplify computations and calculations. So for example, to find the voltage source you want to use in the Thevenin equivalent, what you can do is try to find the voltage between terminal A and terminal B. And that is what we call the Thevenin voltage, which is VTH. Now to find the Norton current, you do a very similar you do a very similar procedure, but how you do it is by shorting the terminals A and B and finding the current across it. So note that this shorting will cause the entire voltage from A to B to change a little because now we have a short circuit, which causes the current to flow through a different loophole. So if you're calculating Thevenin voltage and Norton circuit current, please remember that you should not be deriving for both of the quantities at the same time because one involves shorting, one does not involve shorting. Last but not least, equivalent, we can also find the Thevenin or Norton resistance. Both of these values are actually equal. It's finding the equivalent resistance between the terminals A and B. And when you're finding the equivalent resistance, you also need to zero out the independent sources. So for example, so we'll go through an example about how to find the equivalences later, but make sure you make sure to remember this. Furthermore, remember that the Norton current times the Thevenin resistance is actually directly equal to the Thevenin voltage. So there are actually two ways around which you can find the Norton current. One is that you short the terminal AB as talked about before. The other way is you find the voltage and the resistance for Thevenin circuit, and then divide V by I to get the divide V by R to get the Thevenin current, which is actually similar to the Norton current. And as spoken before, this is because all of these equivalent circuits have the same IV relationship. All right, before we hop into a practice question, is there anything people would like me to clarify? Okay.
Nothing in chat.
Nice. All right, let's move on to a practice problem, which I think it's here. Okay, which we'll just walk through here. So due to the issue of time, we'll just walk through the example question directly. And I'll do this on my notebook. Let's try to pull out the notebook a little. What do I hate technology all the time. Oh, never mind. Okay. If people can see my OneNote, it'll be very helpful. Okay. So let's try to go through this question here, which is the exact one on the slide. So first of all, we'd like to find the equivalent resistance, which is the Thevenin resistance of the circuit shown above, with respect to the terminal A and B, which means that first of all, we're going to zero the sources. So we're going to zero the sources. What this means is that for anything that says zero sources, you need to turn every independent voltage source into a wire, and every independent current source into an open circuit. As for why it's that way, it's because if you use a wire, the voltage difference across a wire is essentially 0 volt, which is equivalent to not putting the voltage source in the first place. If you use an open circuit, the current that flows through an open circuit is practically 0 amps, which means you're not putting a current source there at the first place. So now that we know how to zero our sources, let's zero our sources on the circuit, which would then offer us some circuit that looks like this. And once again, the labeling of the resistor should be the same as before. Okay, so what's the problem here is that if we're going to go through the terminals A and B, first of all, we see that there's two ways that the current can flow through here. One way is we flow from A to B through the R3 loop. The other way is that we flow from A to B throughout this short circuit. What about through R1? Well, here we face a parallel choice between R1 and just a wire, right? But in this case, since currents like human like to take the lazy way out of any situation, we would like to go through the wire directly, which has no resistance at all. So this is why R1 gets skipped. And once again, we call this situation a short circuit. So R1 essentially just does not exist. It just does not exist in the circuit anymore, essentially. So in that case, the equivalent resistance of the circuit becomes R2 parallel R3. And prior, we can also see that R2 is equal to R and R3 is equal to 9R. So essentially, we'll then be computing the parallel of R parallel 9R.
You should explain why R2 and R3 are in parallel.
Okay, sure. So another way to, I just realized this is not Zoom animation. Okay. So another way to write this circuit out after zeroing, which is turning this into a wire, is that we can first put the terminals A and B up here. So we notice that if we flow from A to B, there's two different ways of flowing through. One is through R3 as notated in the blue mark. And the other way is, why does Zoom do this to me? the other way is that we can use another color of the marker to label this, which is going to be R2. And here we have choices, right? We can either go through the wire or we can go through R1. But once again, we'd like to take the lazy way out, which circuits do. And in this case, we follow the short circuit to go through the empty wire, where there's no resistance at all. So there are actually two ways across which the current can flow, presenting us the choice of going through R2, as noted by the red route, and the choice to go through the blue route, which is going through R3. Respectively equal to R and I. Therefore, the entire equivalent resistance now becomes R parallel 9R, which then we can just compute. Here's a shortcut for paralleling, which a lot of you might have learned already, but we'll just go through this regardless. A parallel B itself is actually equal to 1 over A plus 1 over B, which is then equivalent to A plus 1 over A plus B over AB. And we can just reverse the denominator value to get AB over A plus B. So this is a good way to simplify your computations in case in the cases you need it. And last but not least, we'll be able to settle with the equation of 9R over 10R, actually 9R squared up here, which is equal to 9 over 10R. Okay, so this is how we can find the Thevenin circuit. And let me just erase the annotations from here because Zoom is not reliable. Okay, any clarifications? If not, we'll move on to the second part. All right, so that was the first part of this problem, which is to figure out the Thevenin resistance. Now let's move on to the second part, where now we are given another load resistor put right between the terminals A and B. And now we're going to try to find the voltage Vs, given that 1 milliwatt worth of power, which is P equals IV, is dissipated across the load resistor, which is as noted here. Now there are two ways around which, before that, let's write down P equals IV just in case. Okay, so now there are two ways across which you can solve this problem, right? Either you directly solve it by directly trying to derive VAB under the new circumstances, which means you solve and then analyze the entire circuit again. Or you can use the Thevenin circuit that we just derived. So how do we deal with this? Well, first of all, we said that this entire circuit should then have some kind of equivalent called Thevenin, where we have a Thevenin voltage source here, and we have the terminal A here, where we go through a similar equivalent resistance, and we also have a terminal B here. We said that there should be some kind of equivalent we said that there should be some kind of equivalent of the original complex version of the circuit, and that equivalent is the Thevenin equivalent. So now, if we use the Thevenin equivalent directly, we see that the circuit difference between the circuit from part A and part B is just if you add in the RL or not, right? And right between the terminal A and B. So the circuit from part 2 actually does look something like this, where once again we'll use the red marker and note the existence of RL here. This is much easier to analyze than the one in part B. So let's try to work along that. First of all, since we only have derived the REQ here, which is once again 9 over 10R, we'll also like to derive for the Thevenin voltage. So to derive for the Thevenin voltage, we'll then have to use some kind of nodal voltage analysis, which I'll abbreviate the process of here. Essentially, we see that in the original circuit, which is once again Vs being parallel to R1 itself, as well as being parallel to the R2 and R3 current connected in series. Now, here's an important thing about parallel resistors, is that the voltage across R1 is equal to the voltage across R2 and R3 together. And you can tell this by using nodal analysis as well. So for example, say that the node at the top of the voltage source is U1, and here's the ground node. You can see that the difference between this point and this point is equivalent to the difference between this point and this point as labeled on the screen, which are all Vs. So now we can use the voltage divider formula that we just derived from the slide and say that the voltage between AB is equal to the voltage source times R3 over R2 over R2 plus R3, which is then equal to voltage source times 9 over 10. So now we can try to compute for this, where we'll find that the equivalent version of part B circuit is essentially, here we have a voltage source that has the same amount of voltage as 9 over 10 Vs. We have an equivalent resistance that is equivalent of 9 over 10 R, which I think was correct. Yes. And we also have a load resistor here, which is equivalent to 9R. Use the volt. So to find the power that this 9R resistor exhausts, we can use P equals IV. But then we'll also have to calculate for the current across it, which is a little bit tedious. So there's another way to do this, which is that power itself is IV, but the power across the resistor can actually also be derived into I times IR because V is equal to IR. And using that logic, it can also be spoken of as V squared over R. So there are actually a lot of ways to calculate power. And for now, we just choose the easiest one, which actually still happens to be using I times IR. The current across this resistor happens to be the entire voltage over the sum of the resistors in series, which will then be 9 over 10 plus 9 times R is equal to the current across the load resistor. And from you'll see that there's two versions of solution we just wrote out, and you can see the pure difference in the amount of computation you need to do between these different ways of doing. You would rather like to use Thevenin than to use the entire circuit and have to analyze the entire circuit. That is why equivalence is useful. Okay. Any clarifications I should do? Let me see if there is any question in the chat.
Nothing.
Nice. Okay. So we don't have time to go through 1C because there are still 4 other topics waiting to be go over. But the purpose of presenting 1C here is to show you that there's such a thing called a dependent source. What is a dependent source? Is that, well, usually we have independent voltage sources and independent current sources that just supply current and voltage at constant value. It doesn't change the amount of current or voltage it supplies, but a dependent source does. So what you see in the diagonal is usually shown as what you see in the diagonal square here is usually shown as a dependent source. For example, the one we just circled on the screen is called a dependent current source, which, as you can see, the amount of current it supplies is actually dependent on the amount of voltage we get across the terminal A and B. So these kind of things exist. And when you're zeroing sources, dependent sources themselves are not necessarily helpful, because if you zero out the independent sources, then it's equivalent of having those dependent sources just getting potentially zero amount of sources or zero amount of contribution from your already zeroed independent sources. So when you're zeroing the circuit, dependent sources actually don't come to that much of an influence as the independent sources. Right. If there's no clarification I should do, I will move on to the next topic. All right. And as you can see on the slides, we have posted solutions. All right. So now let's go into another topic, which is called superposition. Why would we like to do superposition? Is because, once again, it simplifies circuits, but this time not circuits with very complex resistor networks, but circuits with multiple independent sources. For example, if I at the same time have one voltage source and one current source in my circuit, then the circuit is going to be really complicated. Not to mention if I have two current sources and one voltage source at the same time. But there are algorithmic ways to try to simplify and analyze this circuit. So it is written in the pseudocode here. For a circuit with independent sources from I1 to IK, where I1 is the first independent source, IK is the kth independent source, doesn't really matter how you number this. So then to calculate the current and voltage at some kind of node or across some kind of component, what we'll do is to sum up the result of every of it as across the different circuit versions where we only keep one of the independent source running. So let's go through an example question to see how superposition works in place, which is right below here. Right. So let's consider this circuit and try to perform some superposition of it. So first of all, once again, the thing we need to do here is to first compute for U1 and U2 and U3 when there's only one source intact. And in this case, what we can do for a good tip when you're trying to write your solution is to label your solution by parts. For example, now I'm going to label my solution with part 1 and part 2, so I know which part stands for which sources represent the quantities I'm trying to calculate for. So in this case, I'm going to keep I1 and the part 1 of the solution. The sources that you don't use have to be 0. So we'll end up with some kind of circuit that looks like this, where once again, IA is equal to 1A is kept. We have 4 ohms up here, and a series of 2 ohms up here. We also have 1 ohm here. Once again, IB is 0, so it's open circuit. Ground node doesn't change. So now we're dealing with this circuit first, where we are trying to compute for U1, U2, and U3. So note that here's an open circuit here, which makes the entire circuit situation a little bit more complex than what we would like. But essentially, what we can do here is also just do some nodal voltage analysis. So let's go through an example of how we'll do this. We see that the current at U2, let's call the current here I1 and call that current here I2. I'm noting the arrow mark here, so I'll save the work of doing positive negative sign, but this is not a good demonstration. So what you would notice is that I1 plus I2, which is equal to the current flowing through 1 ohm, is exactly the current that IA offers. And another way to think about this is that your current from the current source IA goes through two different kinds of loops, right? So for example, I'm going to use a different color here to notate it. My current can either go through this longer loop or this shorter loop. And either way, they're going to recombine together to give me the original amount of current they have, which is IA. And as notated by the current source, it's going to be IA equals 1N. So in that way, I know that U2 minus 0 is equal to 1A times 1 ohm, which is equal to 1 volt. Okay, so that is pretty convenient because now we know at U2, we can also deal with U1 and U3. So for now, let's first deal with U1. We know that U1 minus U2 is equal to the amount of current that flows through the 2 ohm resistor here times 2 ohm. And let's note this as I2 ohm left so that we know it's the left resistor. So now that we know it, what we can do then is, oh, actually, it's not just that. Because U1 itself is located way before the 2 loops, which means if I'm going to write the U1 and U2 out here, it's going to look something equivalent to this. Where I have 4 ohm here, I go to U3, and this U3 here is still part of the wire. And now I move on to the right resistor of 2 ohm, and here I have the left resistor to 2 ohm. This entire structure between U1 and U2, these two are equivalent structures. It is also convenient for you to write out equivalent structures during exam so you can simplify the different situations on the circuit. So in this case, we see this happening, and we can determine that the resistance between U1 and U2 is the equivalent resistance of this parallel and series combination resistor, which is equivalent of 6 ohm parallel to ohm. And we're going to make a quick computation here. This is going to be equal to 6 plus 2. And the numerator is 6 times 2, which is going to give me 12 over 8, which is 1.5. Okay, so now I know that U1 minus U2 is equal to the entire current flowing through this series of resistor, because we can simply simplify this network of resistor into one resistor with 1.5 ohms, with the current IA equals 1A flowing through it. So the difference between U1 and U2 happens to be 1.5 ohm, which makes U1 equal 2.5 ohms. Oh, sorry, 2.5 volts, because this is a voltage. Okay. And last but not least, U3 can be calculated in a slightly more different way, which is that we can first derive the current through U1 and U3, and then we can multiply it and use the voltage divider formula to derive for U3. So the computation is a little bit more complicated, which oh, it's already 12:21. Okay, we don't have time to go through this. So U3 itself, I'm just going to directly say the answer here, but it's also derived on slide. It is 1.5 volts. Okay, so now we know from part A that the respective voltages of part A is spoken as below. Okay. Here's the thing about this problem. To do superposition, you'll need to calculate for part 2 as well, which is not a fun thing. But if you observe the circuit and try to zero out IA in response, what you can get is a very symmetrical structure, where if we zero out the source IA instead, we see that the entire circuit now looks like this, which is basically the IA version mirrored. So in this case, while we have a different name for the current source, this new U3 here is actually equal to the previous U1. And this U1 here is actually equal to the previous U3. Because the way that the current flows through an entire circuit doesn't change just because you mirror the circuit around. So this is a symmetry argument for saving work. So essentially for part B, what we see is reflecting the results of the previous part, which at the end, as we sum these voltages up, we'll be able to get that the true values of these quantities will be the added version of U1, U2, and U3, and in turn becomes U1 is equal to 4V, U2 is equal to 2V, and U3 is equal to 4V. This is a quite complex circuit with 2 current sources, but we're able to solve it through using the superposition algorithm. Okay, any question on how superposition actually works? If not, we will be going through the mini lectures for the rest of the topic, and we'll see if we have actually have time to go through the problem. So last but not least, not last, but we have a good topic called capacitor. Now let's talk about the fundamentals of capacitor. So capacitors are essentially components that can store electric charges as current flows through them. And the IV relationship and the energy stored in the capacitor are shown as in these formula, where they're actually each connected to each other. Q equals CV is the most fundamental formula for a capacitor, which stands for that the amount of charge you have in a capacitor is equal to the product of its capacitance and its voltage. Now, what is capacitance? Each capacitor stores charge, but as any container, it has a maximum limit on the amount of charge it can store in itself. Capacitance refers to this maximal capacity of charge that a capacitor can store in itself. So the amount of charge it can store is equal to the capacitance times the voltage across this capacitor. And furthermore, we can use the Q equals CV to derive the following 2 formula, where we see that the energy stored in the capacitor is equal to 1/2 times CV squared, and the current across capacitor is equal to the capacitance times the differential of the voltage across capacitor throughout time. Now, the relationship between Q equals CV and this I equals C dV dt is in fact just differentiating both sides of the equation. Last but not least, we also need a way to determine what the capacitance of a capacitor is. And it turns out that we also have a formula for it, which is C equals epsilon A over D. Epsilon here means permittivity of space in physics sense, but it's also just a property of any matter where as much as a matter has, for example, a frictional coefficient, it also has a coefficient called the permittivity of space, which stands for the amount of charge or the permitted or the amount of charge you permit in between the different spaces of an object. Meanwhile, A here stands for the overlapping area of the conductor plates. It is very important to notice this because at times there'll be weird capacitors that look something like this, where we have conductor of different sizes. In this case, the only parts that count as a capacitor are the parts that overlap, which is this part. So if you're calculating the capacitance of this entire structure, you should only consider the overlapping part, because the fundamental way a capacitor works is by having two conductor plates. If you only have one conductor plate, it does not work as a capacitor. So this is it stands for, is loading a little bit. It stands for the distance between the overlapping area of the conductor plate. And in the scope of 16A, these will most likely still be perpendicular. So your distance should be constant. But also note that there are weird capacitor structures that look like this, where all three of these are conductor plates, but you see that this actually forms three capacitors here. In this case, this kind of capacitor is modeled like a capacitor here on itself, where only two plates overlap, and another series of two capacitors here, where there are two pairs of overlapping plates. So this is another interesting implication of the C equals epsilon A over D thing. It is possible. Oh God. I thought screwed out for some. Space. Oh wait, it just started again. Okay, so this is probably just a Wi-Fi thing.
Right. Okay. Cool.
Okay, let's keep going on. So this is once again, this is how capacitors in parallel and series works out. And I encourage you to look at this on your own time, as well as do this as a practice for derivation. Okay, so here from how capacitors in series will store the same amount of charge. So charge sharing has to do with this kind sharing problems currently. So it is also a good opportunity for you to practice charge sharing. This is a past mentioned question. So far are amplifiers. First of all, we have this thing called op-amps, which are magical things called operational amplifiers. But put in very but it also comes with some interesting properties. For example, the current that flows into what we call a positive any current flowing Okay, let's continue. Nothing happened. So meanwhile, as we see, there is a ground minimum and maximum, so there's no such a good thing.
It must be that your Wi-Fi is like, yeah,
Wi-Fi is on track.
yeah.
Okay, so once again, this is called a comparator. It is an op-amp architecture. Your negative voltage, which is called U minus. The output EECS. As for is somehow a bit confusing.
My goodness.
This is all right, sorry about this. So now we're talking about negative feedback. So negative feedback refers to the phenomenon when the increase of your output, which is V out, leads to the decrease of your which leads to a decrease of your input. And because this decrease of the input is going to be amplified, it is going to cause your output to in turn be decreased. So in summary, if you increase your output, you in effect decrease
And reconnect to,
on.
yeah, and then remember to start sharing again.
Okay.
Perfect.
Yeah. All right. So as we talked about before, negative feedback is when you increase that your op-amp receives is actually the difference. Increases your input voltage. And because your input is the difference between V plus and V minus, this means that while your V plus stays constant, your V minus must have also increased so that your entire feedback in general just means that if you increase your output voltage, it increases your V minus. And this gives it a bit more intuitive sense of why it's called negative feedback. Now positive feedback means the opposite thing once again.
I think 61C actually got shifted to 1 p.m. So we have a little bit of time if you want to go.
Okay. And then afterwards, negative feedback doesn't just stop at knowing what is negative feedback. There are also these op-amp structures that are pretty useful for helping us know how exactly do we amplify a voltage or inverse a voltage by -3 or 3 times. So in this case, the left side of the slide is just repeating something from the original context. And these things are very worthy to put on your cheat sheet because in the case you need your voltage to be amplified by 2 times, for example, it is very useful to have the structure in mind about how to do that. There is a practice problem on this, which we don't know if we have the time to go through. But for now, so these are the practice. This is a particular practice problem about how to design a circuit with capacitor and how to use an op-amp to do that. But in particular, since the review section is going to come to an end, This is assignment from 6.1c. Okay, so once again, here are the review resources. And if you would like to visit some of the CSM practice with a Berkeley email, and you can get access.
We have until 1 p.m. If you'd like to stay around and ask any questions, please feel free to. And we can answer them. So you can put in chat or you can just ask us in person. But yeah, this is